All right, everybody, here is our video on photons and matter, on wave particle duality. Lots of stuff going on here. I guess I should have my pen out. For wave particle duality is really what this video is going to focus on. So we're going to take a look at how do photons interact with matter? How do photons behave like matter? Or how does matter behave like a photon or like a wave, like light, everything like that? Okay. So wave particle duality, essentially what this means is that light sometimes behaves like a wave, and light sometimes behaves like a particle. Right? We call this, when light behaves like a particle, we call that a photon. When light behaves like a wave, we call that a wave. Okay. As we're looking at this, couple of things to consider. So wave particle duality, couple of consequences that this brings. Let's take a look at when things are photons, when they're a wave, versus when things are matter, and how do those interact. So I'll have this as I'll call this wave matter interactions. Okay, wave matter interactions. There are a couple of things that can happen from this. And by a couple, I mean three. Wave matter interactions. 1, 2, 3. Basically, I'm looking at when does a wave interact with matter? Well, there's three options. When the wavelength is bigger than the spacing between atoms. So space between atoms. Another option, when the wavelength is about the same size as the space between the atoms, and when the wavelengths are, you guessed it, less than or shorter than the spacing between all the atoms. Okay. Right, when wavelengths are bigger than the space that there is between atoms or the space that we're given, this is, example, microwave mesh. Right, in our microwaves, we have microwaves are on the order of a centimeter. Lambda is about a centimeter, or 2 centimeters-ish is the average microwave. And then the mesh is on the order of like 3 millimeters, so 0.3 centimeters. Well, the wave is bigger than the mesh, so the wave cannot pass. The wave cannot go through the matter. Waves can't go through the matter. If it helps you to think about this, this is how I think about it. Right? Things can't go through when they're bigger, so the waves cannot pass. Just like in Lord of the Rings, right? Gandalf says, "You shall not pass," and slams his stick down. Because the Balrog, the little fire beast, the Balrog is bigger than Gandalf, so the Balrog can't pass. Waves cannot pass things that are smaller than them. The Balrog can't go past Gandalf, who is smaller than him. Okay. When things can't go through matter, there's a couple of things that might happen that we've talked about. This would be the photoelectric effect can happen. So the photoelectric effect. Another thing that might happen is light gets absorbed or reflected. So we could absorb or reflect light. Okay. Second option here, when the lambda is about equal to the spacing between atoms, this could be either de Broglie wavelength electrons going through a crystal or light incident on a thin slit. So I'll say thin slit over here, because what happens is diffraction. So we get the diffraction patterns. That's the most important bit, right? We get these intensity graphs over space that look like this, all that kind of stuff. That's intensity over spacing x. We get these diffraction patterns. So, right, that happens for a couple of different examples. We can get de Broglie diffraction. De Broglie diffraction. All right, so that's electrons through a crystal. Another way we can do this is like a double slit or a single slit or a diffraction grating, anything like that. That's what happens when the wavelength of the wave is approximately the same size as the space that it has to go through, or the width of a slit. Okay, the third option that we have is when the wavelength is much smaller than the space that it has to go through. What happens here is they just pass through. So it just passes through. And that's it. Right? So this would be like an X-ray. When you get an X-ray, the X-rays just pass right through you because X-rays are a little bit smaller than most things that you have in your body. Gamma rays, for sure, because gamma rays are even shorter wavelengths than X-rays. So that's as short as a wavelength as we can get. Gamma waves, they just pass right through most things. X-rays, right, they can be stopped by like lead. Gamma can't really be stopped by almost anything because gamma waves are shorter wavelengths than atoms. Okay, so this is where danger happens. Gamma rays pass through walls, X-rays pass through your flesh, although all that, I would say good stuff, but it's not really good stuff. Okay, so wave matter interactions. That is one very important section of this video. Another thing for us to consider here, there's this thing called wave-particle duality. This is the main feature of this video, wave-particle duality. In this wave-particle duality, basically this means waves, or light sometimes acts like a wave, light sometimes acts like a particle or a photon. Essentially what AP is going to ask is when we consider light as a wave and when do we consider light as a particle, or like what situations confirm that light acts as a wave, what situations confirm that light acts as a particle. If you remember, this is kind of like our situation that we had with, right, if we had electron slits. All right, so I had this as we've got some electrons incident on a pair of slits here, just a beam of electrons. And our electrons, as our electrons go through and our electrons are incident on the slits, right? Maybe if we observe the screen, we get this diffraction pattern. But if we observe the slits, that all goes away and we don't get the diffraction pattern that we would expect from the wave. So that's what confirms waves happen. If we observe the slits, right, we watch the electrons go through, then we see that the electrons behave nicely and the electrons just go right through. They behave like particles. Okay, so this is just like this. Really, light as a wave, well, we can observe light as a wave when we have light incident as just a bunch of wave fronts on, and I'll make this, we'll do a double slit here, right? Light, bunch of wave fronts on a double slit, and we get these wave fronts on both sides. We get all these interference patterns where, right, we get these maxima, we get the minima. So we get our screen, right, with that. So anytime we observe interference patterns, that means wave. Light is acting as a wave. Anytime we observe an interference pattern, light is acting as a wave. And I'm going to just take this and move it a little bit over so we can have more space to write some other things. Anytime we observe an interference pattern, light is acting as a wave. Anytime we observe an electron getting knocked off an atom, right? So that would be like the photoelectric effect, right? So if we observe light incident on, and this is what we just talked about in the most recent videos, light is incident on a piece of, we talked about sodium is an example, then these electrons fly off and these electrons have some sort of kinetic energy. That, right, anytime we have electrons incident on an atom that knock an electron off, or sorry, photons incident that knock an electron off, that means that we are observing this photon being incident on the electron because that means there's a collision of some sort. Okay, so an example of photon behavior is the photoelectric effect. effect. Okay, and that means photons. So if you can remember, interference creates or confirms that light is a wave. Photons confirm or are confirmed by the photoelectric effect anytime photons and electrons collide. Okay, what we'll do now is I've got one last thing for us to look at. I want to take about 30 seconds to mention this, maybe 2 minutes total, to talk about this thing called wave function. Essentially, a wave function, this is the probability of finding an electron. The probability of finding an electron. Okay, so the wave function, there's like 2 questions on the AP question bank for this. So if you don't know it, that is 100% fine. We have you might have talked about the Schrodinger model of the atom. The Schrodinger model of the atom, and I will say orbitals when I look this up. If we go to images, right? We've looked at the Bohr model, which is exactly like what I drew a couple pages ago. The Bohr model is like this, where we've got a nucleus in the middle, and then we've got orbitals, everything that we've looked at. But one of the other models of the atom we can use is the Schrodinger model of the atom, using this thing called a wave function. Now, this math is differential equations. It's really complex. But essentially, this wave function here, what this shows us is the probability that the electron exists in that space. Because electrons, they're floating around, right? They're buzzing around all over the place. And if we take a snapshot of one instant in time, say we use a camera to just take a picture of the atom and we locate the electron, this graph tells us the probability of where the electrons are. And this is just weird. Essentially, all you need to remember from this is that this thing called the wave function, the wave function of an atom is the probability of finding an electron. Because electrons are not always where we expect them, so we can use this thing called the wave function is the probability that we find the electron there. The wave function is given by this Greek letter called psi. It looks like a trident. P-S-I, psi. So that's the wave function is given by this psi. One last thing to mention here. If this is a graph that I've pulled from an AP question. This is that little psi trident thing up there. Essentially, they would ask for a question like this. They would ask, where's the electron most likely to be found? Well, this is psi, and psi tells us the probability. Almost. Psi tells us the probability of finding an electron there. But its magnitude is the probability, pretty much. What it truly is the probability, or lowercase p is psi squared. So essentially what we look at is where does psi have the biggest magnitude, and that's the highest probability. So if the question is where is the highest probability of finding this electron, where's the highest probability of finding this electron? We would say, okay, where's this graph have the biggest magnitude? Positive or negative doesn't matter because it'll get squared. And at that, we can say here, oh, it's going to be about 1 is the magnitude there. Same with over on this side, but at 2 meters, oh, this is -3. So the highest probability is going to be there because this gets squared, so it'll be about 9 compared to being about 1. So highest probability in this case would be about 2 meters, and that's the answer you'd give. I've only seen this in multiple choice questions and rarely, but I wanted to make sure you had exposure to it, especially with this weird little letter psi. If you forget that and never remember it again, that is 100% fine by me. It's low likelihood it's on the test. The real point of this video is this wave-particle duality, right? Wave-matter interactions. If you can remember the 3 types of wave-matter interactions, it just depends on whether the lambda is bigger than the space it has, is about the same as the space it has, or is smaller than the space it has. The other thing is wave-particle duality. When is light confirmed to be a wave, and that's interference. When is light confirmed to be a photon? And that's anytime you get like a photoelectric effect where electrons jump out of the atom. And that'll do it for this video. I hope you've enjoyed AP Physics 2. You are done now with everything to do with AP Physics 2. Have a great rest of your day, knowing that you've now learned everything that you need to know for this course. I will see you next time in class. Let me know if you have any questions, but have a good one.